Right, let's talk about calorimetry, where we're going to use the law of conservation of energy to measure heat lost, which is going to be equivalent to heat gained in a system. So we need to know what calorimetry happens to be. It's the study of how heat transfers inside of a system. And don't forget that all changes in matter, physical or chemical, are accompanied by a change or transfer of energy. So energy is going to move from one spot in the system to another. And that has to be the case since the law of conservation of energy says that energy is conserved. We need to know a few numbers. We need to know that 1 calorie, 1 little c calorie, notice how that's a lowercase c, is equal to 4.18 joules. In our class, we're going to measure in calories, but other classes use joules and kilojoules very often. And the reason why we like to use 1 calorie is because 1 calorie is equal to the amount of energy it takes to raise 1 gram of water 1 degree Celsius, which is going to make some of our math easier to do later. And then 1,000 little c calories are going to be equivalent to 1 big C calorie, which is also known as a food calorie or a kilocalorie. So how do we actually measure these energy transfers? The first thing you need to know is that the heat that's being transferred can't be directly measured. Instead, we have to measure something that's either in contact with that heat, and it's either going to be gaining the heat or losing the heat. Whoops. So we're going to measure how much heat is gained or lost, and we're going to do that by measuring something else. So like we might be measuring how much heat water gains or how much heat water loses. Typically, we're measuring water. We'll keep going back and forth here. So we're trying to measure how much energy that water gains or loses. To do that, we normally use a tool called a calorimeter. And calorimeters are either very simple, it's just a styrofoam cup nested inside of another styrofoam cup. You can use a lid, and even without a lid, these are actually pretty accurate. Or they can be very complicated, like a bomb calorimeter that's very, very good at isolating the system. Now, both of these are designed to minimize heat being transferred outside of the desired system and into the environment. We want to be measuring all the heat that's being exchanged, and we don't want it to be exchanged to places that we don't want it to be exchanged to. Hence, items that act like coffee cups work great. Again, we're going to be measuring the water normally because it's really easy to measure how much heat water either gains or loses. So devices that minimize heat exchange to surroundings are really good calorimeters. And again, nested styrofoam cups that you would just have hot chocolate or coffee in work very, very well, specifically for our purposes. So we have some equations then that we can use to make these calculations. And the first general one that we just need to remember, this is the law of conservation of energy. It says heat loss is equal to heat gained because heat is conserved. So we can write that as delta H, change in heat. That's the heat that's lost is going to be equal to change of heat that's gained. And then delta H is equal to mc delta T, where m is mass, c is something called the specific heat capacity of the substance, which describes the resistance of that substance to change temperature. High capacity for heat means it's really hard for that substance to change temperature. Low capacity for heat means it's really easy. So metals, since they're good conductors, have low specific heats. Water is actually a really good insulator, so it has a relatively high specific heat capacity. And then delta T is going to be change in temperature. So we can see that we have delta H, change in heat, is equal to mc delta T, mass times specific heat times the change in temperature. Make sure that you have your change in temperature positive, so basically absolute value your temperature for most of our problems, and then make sure that we're also measuring in Celsius. Since heat loss can be equal to heat gained, and we already know that delta H is equal to mc delta T, we can just substitute mc delta T in place of both delta H's, which leaves us with mc delta T is equal to mc delta T. And again, we're going to have the mass, specific heat, and change in temperature, but this time it's going to be of substance 1 and substance 2, hence the subscripts that you see right here. We can rearrange these equations to solve for a specific variable. So just for example, if we're doing mc delta T is equal to mc delta T, all of these are going to be about one item. So it might be about the water, and then this might be about a piece of metal. If we wanted to solve for the specific heat of the metal, we could rearrange this equation. And we would do that by dividing by m and delta T on the left of the metal, m delta T on the left for, we'll move the m and delta T on the right over to the left. That crosses these off, crosses off, crosses off. So we're left with mc delta T. Remember, these are all for water, divided by m delta T. These would be of the metal, is equal to the C of the metal. So, knowing this equation, delta H equals mc delta T, and then the equation mc delta T equals mc delta T for two different substances, you can solve just about all of the calorimetry problems that we're going to encounter in our class.